Good afternoon, everyone. I'm Suraj, a TA for Data 100, and today we're going to be walking through discussion 12 from the spring 2019 iteration of the course. Okay, so discussion 12 sort of just goes over a lot of different topics we saw throughout the semester. So there's sampling, some visualization questions, estimation, gradient descent, and then bootstrapping, and even some distributed computing. But first, before we get into all that, let's start with number one, which deals with sampling. Okay, so I won't read the question. I'll let you pause the video right now or something to read the question. What I want to do before we start answering any of the specific questions is sort of give an overview of what exactly this sampling technique really looks like. Okay, so let's go over here. Okay, and make sure you understand. Make sure you've read this before continuing. So we're told that we have 3 states. Okay, and each state there's 10 towns, and the population in each state is evenly distributed amongst the 10 towns. Okay, so state A has 100 people. That means there's 10 people per town. And we're also told that each town has an equal number of male and female voting adults. So that means there's 5 males and 5 females for each town in state A. Okay, and we're also told our survey is administered by randomly sampling 3, 8, and 12 voting adults from each town in each state. Okay, and so it's not worded perfectly, but what this really means is we're sampling 3 people from each town in state A, 8 people from each town in state B, and 12 people from each town in state C. So we're selecting 3 from each town in state A. So similarly, state B has 200 people, so that's 20 per town, which means we have 10 males and 10 females, and we're selecting 8. Lastly, state C, we have 300 people, 30 per town, which means we have 15 males and 15 females, and we're selecting 12. Okay, so we have 10 towns in state A, 10 towns in state B, and 10 towns in state C. And what we're told in this sampling setup is that we're sampling 3 people from every town in state A, 8 people from every town in state B, and 12 people from every town in state C. So to answer first, what type of sampling plan is this? This is stratified sampling, where the stratas are the towns. Okay, because we're sort of dividing up our country into 3 states, and then furthermore, we're dividing those states into towns, and we're doing a simple random sample within every single town. Okay, so we're doing stratified sampling. B, how many strata are there? There's 30, right? Because there's 3 states, 10 towns per state, and we're sampling from every single town in the country. So that means there's 30 strata. Okay? But A and B were sort of just a setup to part C. What's the probability that the sample generated from this sample strategy will comprise of all females? Okay? So what I want to do before answering that question directly is first zoom in to just one single town in state A and see what's the probability that all of the people I sample from that one town in state A are all female. And if we do that, it shouldn't be too hard to generalize to all of the towns in state A, and then all of the towns in B, C, and then combining them all together. Okay, so let's zoom in. Let's zoom in to a single town in state A. So one town in A. What's the probability that this happens? Well, it's the number of ways we can sample 3 females divided by the total number of ways we can sample 3 people from this town, right? How many people are in each town in state A? 10, and we're selecting 3 of them. So the total number of ways that this can be done is 10 choose 3. Okay? Now our numerator is the number of ways we can sample all females. How many females are there in each town in state A? 5. We want to choose 3 of them. So we have 5 choose 3. So this probability, 5 choose 3 divided by 10 choose 3, is the probability that in one specific town in state A, we happen to sample all females. Okay, you can also think of this as being slightly different. We can think of this as being first, or we can arrive at the same result by first calculating the probability that the first person I select is female times the probability that the second person I select is female times the probability that the third person I select is female. For the first person, it's 5 over 10, right, because there's 5 females left in a town of 10. The next is 4 divided by 9, right, because now there's 9 people left in the town, 4 females, and then times 3 over 8, because now there's 3 females left and 8 people total. Okay, these happen to work out to the same result. I personally think the first one is a little easier to comprehend and write down, so I'll stick with that, but you should know that these are equivalent if you work out the algebra. They're just slightly different interpretations, okay, but they're both fine. Okay, so we found the probability that for one town in state A, we happen to sample all females. Now we need to extend this to all towns in state A. And so we can assume that all of these towns are sort of independent, and so what we do is just multiply this probability by itself 10 times. Okay, so we have the probability for town 1 in state A times the probability for town 2 in state A, so on and so forth. So we multiply this by itself 10 times. Oops. Okay, cannot draw today. So we have this to the power of 10. So this is not just one town now, this is all towns in state A. We have the probability for one town multiplied by itself 10 times. Okay, when we did this in in-person discussion, a lot of students said multiply this by 10 instead of raising it to the power of 10. And that's not quite right, because multiplying it by 10 is the same as adding itself 10 times. And there, the probability might end up being greater than 1. Okay, you add when you have a bunch of disjoint cases, or in other words, when you have a bunch of different ors. Here we have a bunch of ands, right? We want the probability that we sample all females from town 1 in A, and we sample all females in town 2 in state A, and so on and so forth. Okay, we can pretty easily extend this to state B. Our denominator in this case would be 20 choose 8. It's all the ways we can choose 8 people from a group of 20. And the numerator is 10 choose 8. We have 10 females, select 8 of them. And that's for one town. So for all the towns, it's that to the power of 10. And lastly, for state C, very similar. Denominator would be 30 choose 12. Numerator, 15 choose 12. That's for one town. For all of them, we raise it to the power of 10. Okay, so now we have individual probabilities for all towns in state A, all towns in state B, and all towns in state C. So now the probability that all selected are female is just the probability that all female in state A times the same thing for state B times the same thing for state C, right? Because it's an and these things are sort of independent. So what we can do is just multiply the 3 previous results we just had. So we have 5 choose 3 over 10 choose 3 times 10 choose 8 over 20 choose 8 times 15 choose 12 over 30 choose 12, all to the exponent 10. Okay, and so now this final result we have here is the probability that using this sampling strategy, all of the people we happen to sample end up being female. Cool. Okay, so now number 2, we're given a bunch of different scenarios, and we're told to choose one of these different types of distributions that would probably best describe the information given in the question. Okay, so let's do it. A, sale price and number of bedrooms for houses sold in Berkeley in 2010. So there you might think, oh, we have 2 numerical quantities. Why don't we use a scatter plot? But you have to look a little deeper for this one. The number of bedrooms for houses is almost like a discrete label, right? Almost all houses will have, 1, 2, 3, 4, 5, or 6 bedrooms. And if you plot out what this might look like, it'd be very overplotted on each of these columns almost, right? So the houses with 1 bedroom, you'd have a bunch of dots here. It would be sort of hard to tell the distribution. Similarly for 2 houses, 3 houses, and so on and so forth, right? And so it doesn't really make sense to use a scatter plot because there's only so many discrete integers that could take on, there's only so many values that the number of bedrooms a house has could be, right? So for this, it really makes sense to use side-by-side box plots. Okay, so for the houses with one bedroom, you can have a box plot for its sale price distribution. For the houses with two bedrooms, you could have a box plot for its sale price distributions, and so on and so forth. Okay, and that would be a little cleaner and easier to read than a scatter plot like this due to overplotting. Okay, B, the sale price and date of sale for houses sold in Berkeley between 95 and 2015. There we have two continuous numerical values, so a scatter plot seems okay. Okay, and it doesn't really make sense to use a line plot here, even though we have one of our variables being time, because we're just given a lot of information, right? Here are a bunch of houses, here are the years they were sold in, and here's how much they were sold for. It's not saying that this is the average house sale price in 95, this is the average house sale price in 96. We have more information than that, and so in order to convey all of that, a scatter plot is probably best. C, infant birth weight in grams for babies born at Alta Bates Hospital in 2016. So there, since we just have a single continuous numerical value, what we probably want to use is a histogram. Right? If instead, and we're told that we're given the birth weight in grams, which is pretty granular, right? So we would have enough information to make a histogram. Whereas if we were given the birth weight in like kilograms or something, there wouldn't be too many different values. Okay, so there maybe we could use like a bar plot or something. But since we're given a pretty granular measurement, a histogram seems like it would make sense. D, mother's education level, so the highest degree held for students admitted to Berkeley in 2016. So for this, we have just a few discrete labels, right? So like, let's just say high school, undergrad, master's, PhD, and something else. And for each of those, we just want to visualize the number of students that fall into those categories, right? So our plot might look like something like this: high school, undergrad, master's, PhD, and for each of them have some sort of count, the number of students whose mothers had that highest education level. So for this, we could have a bar plot. Might have accidentally said box plot. I meant bar plot for this one. Okay. E, SAT score and high school GPA of students admitted to Berkeley in 2016. Again, this one's a scatter plot because we have two continuous numerical quantities. For example, the x-axis could be SAT score, y-axis could be high school GPA or something. So that could be scatter plot. F, the percentage of female students admitted to Berkeley each year from 1950 to 2000. So this one, it makes sense to use a line plot. Okay, so our x-axis could be time, and our y-axis could be percentage, and then we could have something that looks like, I don't know what the numbers look like, but something like that. Okay, there, it would make sense to use a line plot, because for each year, we just have one number. Okay, for each year, we have the percentage. So a line plot in this case probably makes the most sense. A line plot. Okay, and now G, the SAT score for males and females of students admitted to Berkeley from 1950 to 2000. Okay, so first, on a larger level, if we just care about the average SAT score for males and females each year, we could use overlaid line plots. Okay, so for example, if we had our y-axis be SAT scores, we could have one color represent the average male SAT score for each year, and another color represent the average female SAT score for each year. Okay, but there we'd only get to see the average. Okay, but it sort of implies to us in the question that we have a little more information than that. We have for each student admitted, we have whether they're male or female and their SAT score. So what we could also do is have this would be a very large plot, but we could have many side-by-side box plots, right? So one for every year, and for male and female, we could have a visualization of the distribution of students that fall into that category. So what I mean by that is, so for example, we could have like a box plot for, 1950 males admitted to Berkeley, and then another for 1950 females, 1951 males, blah, 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 until whatever. What are we told? 2000, females, and we could have whatever the distribution is. Okay, so we could have many of these different box plots, and the reason why this is probably more preferred is because it gives us more insight into these distributions every single year, whereas if we had to do an overlaid line plot, we'd only get to use the average for each of these two values per year. Okay, so the one we'll prefer is side-by-side box plots. And I think that wraps up number 2. Okay, so now let's move on to number 3, which deals with estimation. And so we're told that suppose we want to predict a donkey's weight, yi, from its sex alone. And there's 3 sexes of donkeys. So a donkey sex could either be gelding, which is G in this case, stallion S, or female F. And our model is yi is equal to beta F times dFi plus beta G times dGi plus beta S times dSi. Okay, and we're told that according to the donkey's sex, the corresponding D value is equal to 1, and the other 2 D values is equal to 0. So for example, if donkey I is a female, DGI and DSI are set to 0, the only thing that matters is beta F, because in that case, DFI would be set to 1. Similarly, if a donkey is a stallion, DFI and DGI are set to 0, and DSI is set to 1, so our prediction is a constant model, but it's sort of like 3 separate models, right? We have one for the female donkeys, one for the gelding donkeys, and one for the stallion donkeys. Okay, because the beta S and beta G don't impact our prediction for the female donkeys, and same for the other 2. Okay, so what we want to do is prove if we have this loss function, which is really just sum of the squared losses, then the loss minimizing value beta hat F is the mean weight of all of the female donkeys. Okay, so the key insight is that it's not the average weight of all of the donkeys, it's only the average weight of the female donkeys. Okay, but this sum, the way it's written, is over all of the donkeys. So there's some sort of logic we're going to have to use to be able to say that the optimizing value only has to do with the female donkeys. Okay, and the insight we'll make is what I earlier mentioned. This is really 3 separate models bundled into one, right? So for example, suppose donkey I is a female donkey. Then the loss for that specific point, since DGI will be 0, DSI will be 0, and DFI will be 1, the loss for that specific point is just yi minus beta F squared. Okay, similarly, if donkey I is a stallion, the loss for that point is just yi minus beta S squared. And if it's a gelding, then the loss for that point is yi minus beta G squared. So what we can really do is break our loss function up into 3 separate sums. One for the female donkeys, one for the stallions, and one for the geldings. Okay, so let's do that. So we can say our loss function is really equal to the sum over all female donkeys, so all female donkeys, of yi minus beta F squared, plus similarly over all geldings of yi minus beta G squared, and then over all stallions, yi minus beta S squared. So our loss function is really these 3 separate sums. And what we want to do is find the optimal value of beta F. So what we do is take the partial derivative with respect to beta F. The latter 2 sums are irrelevant because they don't involve a beta F. So really, this is the partial derivative with respect to beta F of this sum, which is, as we've seen on numerous occasions in this course, use the power rule. So we have 2yi minus beta F times -1. And to find the optimal beta hat, what we do is we take the derivative, set it equal to 0, and solve for the beta. So we can divide by -2, and we're given that the sum over F, or F being the female donkeys, of yi minus beta F is 0. We can break this apart into 2 separate sums. The sum of the yi's minus the sum over F of beta F is equal to 0. what does this second sum mean? The sum over f of beta f. Well, beta f is just some constant, and we're summing it for each time we had a female donkey in our original set. Okay, right? Because the sum of a constant n times is just n times the constant, right? As we've seen before. So this latter sum is really equal to beta f times the number of female donkeys. Okay? And now at this stage, if we do a little bit of rearranging, we get that the optimal beta f is the sum of the weights of all female donkeys over the number of female donkeys, which is the average weight of female donkeys. Right? The sum of all the weights divided by the number of them is the average. And so we've concluded the proof that the loss minimizing value of beta hat f is the average weight of the female donkeys. And you could do the same thing to show that the minimizing values, the loss minimizing values for beta g and beta s are the corresponding average weights of gelding donkeys and stallion donkeys. But that's number 3. Okay, now moving on to the optimization portion of the worksheet. So in number 4, we're given a Python implementation of gradient descent, but we're told there's something wrong with it. So taking a look, first we initialize theta to be our initial guess, theta naught. That's fine. For t in range, essentially maximum iterations plus 1, that's fine. The gradient is what we get when we call the gradient function on the current value of theta and x and y, that's fine. And so there are 2 mistakes with this implementation. So the first one is what we're returning. This implementation returns the gradient, but we don't really care about the gradient itself. The gradient is just a tool to help us find the theta that minimizes the loss function. What we really care about is the theta. Okay, so that's one mistake. The other mistake is the update equation, so line 10. Okay, gradient descent is supposed to be an iterative method, right? Which means it improves on the previous guess at every time step. But here, the way it's written is not iterative, right? Because we're using theta naught, but theta naught shouldn't be part of our calculation at all. What we should do is iterate on theta at each step. So this is really supposed to be theta. Okay, oops, there we go. So that's part of it. So theta is equal to theta plus 1 over alpha times the gradient. Not quite. So it shouldn't be a plus, right? We want to move in the opposite, we want to move opposite the direction of the gradient, right? So that we arrive at a global minimum. So this should be minus. And we're told that alpha is the learning rate, okay? And the expression for gradient descent is our estimate at time step t plus 1 is our estimate at time step t minus alpha times the gradient of the loss function at time step t. Okay, where alpha is the learning rate. Here we have 1 over alpha, which isn't quite right. So we need to change this to alpha. Okay, so a little more concretely, what were the mistakes? Line 10 should have been theta is theta minus alpha times the gradient. In line 11, it should just be return theta. Okay, when we did this discussion in person, a lot of students didn't think that 1 over alpha was a mistake. And that's because it's easy to confuse the 1 over alpha with what is called the decaying learning rate, as we've seen in some of the examples in lab. And the decaying learning rate is when alpha decreases on successive time steps, right? We had, with the decaying learning rate, alpha would be something like 1 over I plus 1. Okay, and I guess if we're using t here, that should be a t plus 1. Which means on successive time steps, alpha gets smaller and smaller and smaller because we're assuming we're getting closer and closer to the optimal value and we don't want to overcorrect too much. But whatever 1 over I plus 1 or whatever 1 over t plus 1 is, that's the value of alpha, okay? And the learning rate is alpha itself. So that's one thing to keep in mind. Alpha is the learning rate. You don't do 1 over alpha, it's just alpha. Okay, so that's number 5. Now number 6, suppose you're given a data set of scalars xi, yi with endpoints, and you have some model where B is the model parameter, and you're using this following regularized empirical risk. Okay, the notation's a little unconventional. I think in this question, theta of xi just represents whatever our model is, and we're assuming there's some beta involved. Part A is asking us, what type of empirical risk is this? Okay, so we can sort of do this by process of elimination. So it can't be option D because it's not Huber risk, and lambda regularization isn't a thing. It's kind of just an option in there to trip people, I guess. So it's not D. It's also not C because the regularization is L2. We have beta squared, right? And beta is just a single scalar here. So yeah, that's more L2 regularization as opposed to L1. So it's not L1. And now the question is it mean absolute error or mean squared error? Clearly, there's a squared up here, so it's mean squared error. Okay, so the correct option is B. Now in part B, we're told that suppose we choose the model, our expectation of y given x is beta times xi cubed. Using this objective function, derive the risk minimizing estimate for beta. So we can come over here and do that. Okay, so now let's say our loss function is really 1 over n times the sum of I going from 1 to n of yi minus beta xi cubed squared plus lambda beta squared. Now what we want to do is, as we did in number 3, solve for the optimal beta. Okay, and so this is a sort of process that you should be comfortable with going into the final exam. So let's do it. So how do we do this? Well, we take the partial derivative with respect to beta and set it equal to 0. So what's the partial derivative in this case? Well, it's a sum, so it's going to remain a sum. And just for brevity, I'm not going to write the i's equal 1 to n. I'll just write it as a sum. Now what's the derivative of this term with respect to beta? Well, it's 2 times yi minus beta xi cubed times the derivative of negative beta xi cubed, which is just negative xi cubed, plus now the derivative of lambda beta squared with respect to beta. I believe that's 2 lambda beta. Okay, and what we want to do is set that equal to 0. So now let's do a little bit of simplifying and rearranging. Okay, so one thing we note is that we can divide both sides by 2 because there's a 2 here. So we can sort of ignore those. And so what we have is 1 over n times our sum. Now let's sort of combine like terms over here. Okay, so we have the sum of negative yi xi cubed plus beta xi to the 6 plus lambda beta is equal to 0. Okay, and so now I can separate this into 2 separate sums. Okay, so I have 1 over n times the sum of beta xi to the 6 minus 1 over n times the sum of yi xi cubed plus lambda beta is equal to 0. And so what we'll do is separate the terms with beta to be on the left side, without beta to be on the right-hand side. Now, and I can also pull out the beta from this first sum, okay, because beta is just a constant. So I can put the beta out here. Okay, so now on the left-hand side, I can move this term to the right-hand side first. So I'll have 1 over n times the sum of yi xi cubed. Right-hand side I'll have beta times 1 over n times the sum of xi to the 6 plus lambda is equal to whatever's on the right-hand side. So now for beta, or beta hat, I just divide both sides by this. So I'm left with 1 over n times the sum of yi xi cubed divided by 1 over n times the sum of xi to the 6 plus lambda. And just to be complete, I can add the indexes in here. And now this is the value for beta hat. Okay? It does look like it kind of came out of nowhere, but it might look slightly familiar if you remember one of the results from a little earlier in the semester, when we used also squared loss without regularization. So squared loss, and our model was something like yi was just equal to beta times xi, so without the cubed. the optimum beta hat ended up being the sum of xi times yi divided by the sum of xi squared. Okay, and you can sort of see the parallels between this earlier result and the result we have here. We really just replace all the xi's with xi cubed. And instead of having xi squared on the bottom, we have xi to the 6. It's a little different because now we're using regularization as well. But yeah, it's also not really required that you remembered this result from earlier. I'm just saying if you did happen to remember it, those are the parallels. But if this sort of appeared on the exam, you'd be expected to go through this entire process. Okay, you're not supposed to remember earlier results like that. Okay, so that is number 5. Okay, now on to the last few questions in the worksheet. So first, some inference true and false. So A, suppose we have 100 samples drawn independently from a population. If we construct a 95% confidence interval for each sample, we'd expect 95 of them to include the sample mean. So that's actually false. And it's because this question doesn't really make any sense. We use the sample means to create our confidence interval. Okay? So all of them will include the sample mean. What confidence intervals really say is that if we construct many 95% confidence intervals, we'd expect 95% of them to include the true population parameter. Okay? So if this instead said population, then it would be true. But since it says sample, it doesn't really make any sense because we're using the sample means to create our confidence interval. Okay, so that's false. And then B, we often prefer a pseudo-random number generator because our simulation results can be exactly reproduced by controlling the seed. And yeah, that's true. That's why oftentimes in assignments, both in this class and other classes, you'll see things like np.random.seed and put a number there. And that's because while the results are random, if you restart your notebook and run all, you'll get the same results. But if you change the seed value, you'll get different results. And that's just so that when we auto-grade it, or someone else wants to take a look at your results, they can get the exact same results, even though they were random. It's sort of like fixing what your randomness will be. So that's true. Now 7, suppose we have a pandas series called the POP, which contains a census of 25,000 subjects. So that's like our population information. And we also have a simple random sample of 400 individuals saved in the sample. And what we want to do is get 10,000 bootstrapped estimates for the median. Okay, so one thing to note is that the POP, that variable, will not be used at all, right? Because when we bootstrap, we're under the assumption that we don't have access to the population at all. Otherwise, there'd be no need to do estimation because we have all of the information, right? So all of our sampling and resampling, should be done from the sample. Okay, so what we're going to start off with is the sample, which is our bootstrap population, but also that initial sample that we have. We're going to sample from it, and we're going to sample with replacement. So replace will be true. And how many times are we going to sample from it? Well, whatever the size of the original sample was. Since there's 400 values in the original sample, we're going to resample 400 times with replacement. Okay? And again, if replacement were false, then each of these resamples would be equal to the original sample. Okay, that's why bootstrapping only makes sense if you do with replacement. Okay, and so now we have all of these samples, and the parameter we want is the median, the statistic rather. And so we do dot median for j in range. Now, how many times do we want to resample and compute a median? We're told we want to do that 10,000 times. Okay, so for j in range 10,000. So to repeat, what we're doing is we're starting off with our sample, resampling from it 400 times with replacement, and computing a median. So we do that once, and then we repeat that 10,000 times. Then we'll have 10,000 different medians, one for each resample, and we'll compute a confidence interval with that, or do whatever else we want to do. Okay, so that's number 7. Lastly, number 8, now we're talking about distributed file systems. Suppose we have 2 files, A and B. So A consists of 4 blocks, A1, A2, A3, and A4, and B has 4 blocks, B1 through B4, and we're sort of given this layout of which blocks are in which machines. So in part A, if we were to lose machines M1, M2, and M3, which of the files would we lose? So now let's pretend M1, M2, and M3 don't exist. essentially what we need to check is that all 8 of these blocks we still have. Okay? Do we still have A1? Yeah. Do we have A2? Yeah. A3? Yeah. And A4? Yeah. So we wouldn't lose file A. So we still have file A, because all 4 of the blocks that make up file A we're still able to access even if we don't have machines 1, 2, and 3. Now, can we access all of the blocks in file B? Also, yes, because we have B1, 2, 3, and 4. So we still have file B, and therefore the answer for this one is C. We would still be able to load both files, because even if we lose the first 3 machines, we still have every single block in A and B at least once. Okay, so the answer to that one is C. Part B, if each of the 6 machines fail with probability P, what's the probability we lose block B1? Okay, so now let's look at which machines actually contain B1. So machine 1 has a B1, machine 2 has a B1, and machine 5 has a B1. Okay, so whether or not machines 3, 4, and 6 fail are really irrelevant to our problem. Okay, because all we care about is whether or not we can restore B1, and the only time we can't restore B1 is if machine 1 fails, 2 fails, and 5 fails. Okay, so that's the only scenario when we can't restore B1, because if only 2 of those fail or 1 of them fails, one of the machines remaining would still have B1. Okay, so the probability we lose block B1 is just the probability that 1, 2, and 5 all fail. Each of them fails, assuming independence with probability P. So the probability that all 3 of them fail is just P times P times P, which is P cubed, which is option B. Okay, so I think that wraps up number 8, which means we're done with the worksheet. If you're studying during dead week or finals week for the spring 2019 final, when I made this, good luck on the final, and feel free to post any questions on Piazza. Good luck.